Okay, so I'm going to talk about trace refinement relations. This is joint work with Timos Antonopoulos at Yale and Chanh who's at Stevens. So programs are constantly changing. There are new features being added, optimizations, bug fixes, but also maintenance and refactoring. And really we can think of code these days as being an evolutionary process as inspired by the agile approach. And so it becomes important to be able to reason about the differences between two versions of a program. And we'd like to go beyond the syntactic level of diff, but of course this is a very difficult problem. On the one hand, a small change, maybe a single line of code, could have a huge impact on the semantics of the program, whereas on the other hand, many lines of code could be changed with no effect, such as in refactoring. And in recent years, or more than recent years, researchers have turned towards embracing this change, as we've seen from other talks in this session. It works well because you can engage with the programmer, and the old version of the program acts like an informal specification from which we can compare against for the new version. And so there's a lot of work in this area. There's works on semantic differencing, Shivendu Lahiri and the SymDiff tool. There's too many to go into, but so I put some of them up here. There's also the state refinement relations of Nick Benton and Hong-Suk Yang, who did it for separation logic. And so there's really a lot of work around this area. So let me make it a little more specific with an example here. So here's a program. You can think of it as maybe a simple server that has this outer loop that's going to iterate. And inside the body, it will receive a message. And then if logging is enabled, it will perform a log. And then depending on whether the message is valid, it will construct a reply, and then it will send it back, and then maybe do some more logging and decrement X. So now imagine a programmer has changed it to this slightly different version, which again is about receiving messages. But this time, once it receives the message, it does an authentication check on the message. And then only if it was an authorized message will it construct a reply and send it back. So if we look at these programs, we may want to try to see how they're similar and what ways in which they're different. And of course, there immediately jumps out similarities between them. There are some events in the program on the left that are the same as the program on the right, such as the receive and the reply events. There are also some events on the left that are the same as the ones on the right, except the conditions under which they happen are different, such as the conditions for logging on the left versus on the right. And then there's also events on the left that just don't have an analog in the program on the right. But when we look at these differences between programs, we'd like to know a number of things, such as what are the conditions under which they behave the same? When maybe they have certain conditions where the logging is the same, or maybe they have the same send-receive message pattern. And we'd like to be able to specify these kinds of properties. So to give you a kind of high-level picture of the approach, we take a trace-based approach to the problem, and we think of a program as being a collection of different classes of traces. So on the left, I've sort of drawn a rough diagram of a program, and the shaded areas, different shades of gray, illustrate different classes of traces through the program. And we can do this for both the programs. And then what we can do is once we take a class of traces from the left program, such as in the darker gray, as well as a class of traces from the right program, then we can correlate them together. And then we can do this for every class of traces in the program in order to show a notion of inclusion or equivalence. So, and then when we get down to the individual trace classes, we may have to further correlate events at the atomic event level, so we need a cross-program binary relation. So that's I've left a lot of details out, but that gives you a high-level picture. Towards this strategy, there's a number of challenges that we need to address. First, I haven't told you at all what a trace class is, and what we're going to describe is a way of representing them using clean algebra with tests. Then we will present our formal notion of a trace refinement relation, and then discuss how these can be automated through algorithms and tools. So briefly, clean algebra with tests is a convenient amalgamation of clean algebra and Boolean algebra. So the clean algebra part lets you describe string-like things with concatenation and iteration and union. And that's useful for representing statements and events and control structures. Meanwhile, the Boolean algebra lets you talk about different conditions and different branching. So there's a standard translation that's due to Koskinen, where you can take a program and represent it as a Kleene algebra with test expression. So what you do is you start with your program statements and then introduce a symbol in the cat that corresponds to each one of them. So I'll write capital A for an event symbol, and I'll subscript it to show which statement it corresponded to. So we start like that, and then when you have a control structure like a while loop, that can be represented using the Kleene star, where we put the condition, now represented as a Boolean test symbol, so that I'll use a lowercase b, inside the parenthesis, and then on the outside of the loop, the negation. So in cat, negation is represented by overline. So this translation works pretty well. Of course, it's a syntactic approximation, and ideally, we'd like something a little bit better. So for example, if an infeasible path is in it, this syntactic translation will directly translate the path. So one of the things we do in the paper is describe a different translation that's more semantic, where we use a two-layer abstraction. So first we take the program, then we run an abstract interpretation on it to get abstract states, and then we go from those abstract states into the Boolean subalgebra of cat. There's some details to be worked out in terms of refining abstractions and combining abstractions, which are in the paper. So let's go back to this example and see how it would work. Again, we're going to try to translate this program into a cat expression. So we use this while structure represented with star, and we start to introduce test symbols. So the A test symbol for representing the condition of the loop. And then we start to introduce action symbols for the statements, such as receiving. Conditionals are represented using the OR in Kleene algebra, where we introduce the symbol B to indicate whether or not L equals true, and the negation for the unseen else branch. And we continue in this manner until we've constructed a full cat expression that represents the entire program. And of course, we could do something similar for the other program, and then here we get K2. So this is convenient because now we've gone from a program to an equational theory that's easier to work with in many ways. Okay, so now back to the question of how these programs relate. So inclusion here doesn't hold. It's not the case that K2 is contained within K1 using cat containment. And we know this, of course, because there was some logging in C1 that was not in C2. There was also authentication failures in C2, and that notion of authentication was not in C1. But we still would like to know what behaviors of C2 are in C1 and how to sort of correlate events and know are there conditions or circumstances under which they behave the same. So going back to the programs, imagine if we took executions of C1, but now just focused on the ones where we only received valid messages. And moreover, let's say that we assume that logging is disabled at the moment. So we can actually instrument these conditions into the program and rerun an abstract interpretation and then obtain a much simpler description of the program, which is written here on the bottom of the slide. So this is sort of focusing on certain classes of traces of C1. And we can do the same thing for the other program. So again, we'll focus on only receiving valid messages, but also only considering the ones where it authenticated okay. And again, we instrument these conditions, run abstract interpretation, and then we obtain another simple trace class description for program C2. So now we have these two cat expressions, the first one for the first program, the second one for the second one. And this is what we use to describe classes of traces or trace classes of behaviors from these programs. And in fact, we can represent these using intersection. So what we can do is take the overall cat expression for the whole program C1 and intersect it with this restriction, R1. So R1 here is kind of like from a temporal logic analogy of always logging disabled. I won't go through the details of that. But we can similarly restrict the other program to say always authentication succeeds. And we can write down the corresponding cat expression that corresponds to that. So then we can do is take these restrictions, they're kind of like filters, and intersect them with the original program's cat expression. And ask the question, is it contained within the other? Now do we know that once we perform these intersections, do we have them to be equivalent? Well, not quite, because there's this K check event that was in K2 that wasn't in K1, as you can see up on the top. But we've already focused on executions where authentication succeeds. So in some sense, it's sensible to ignore this check event. And we can do that by introducing a hypothesis into the cat, which says that this check event is equivalent to 1, which basically means skip in cat. So now we ask this question again. Under this set of hypothesis in the subscript there, does this equivalence hold or inclusion hold? And indeed it does. And so now we have a triple. And this triple is the first piece of a trace refinement relation. Notice here that the elements of the tuple are not states, but rather descriptions of trace restrictions. And we can do this then for all the various behaviors of K1 and try to correlate them with behaviors in K2. And if we do that, then we can assemble our trace refinement relation, which is denoted with this capital T. And then we say that the K1 is trace refined by K2 if you take any one of the tuples in it and the inclusion holds. Now, I've kind of been loose about the distinction between inclusion and equivalence. You can define it any way you like. There's the formal details of that can be found in the paper. Also, there is a weak notion of equivalence, which is fairly straightforward, and because you can always just sort of introduce axioms to reduce everything to skip. So it more comes down to a question of utility for understanding how they relate. So this theory that we've come up with is also compositional. I won't have time to go into the details, but this will enable, ultimately we hope, an incremental program analysis. So you can reuse a refinement relation in many different contexts. And the goal is to be able to reason locally around the area where the program has been edited. So in the paper, you'll see the different notions of compositions as well as corresponding theorems for them. So that's the specification of these relations between programs. And now we turn to the question of whether we can automate this and can we discover these relations automatically. And the answer is yes. In the paper, we describe an algorithm that's able to generate these trace refinement relations. Here's a sketch of it. There's also a soundness proof. But for the purpose of illustration, I'll instead go through an example to show how the algorithm works. Okay, so here's another example of the error handling portion of a web server. So on the left, you see THTTPD is a sort of simplified version of it, where when there's an error, it clears the connection and then shuts down. If there wasn't an error, it updates the statistics. And then the Meerkat program is a derivation of THTTPD that also has a feature of a keep alive. And in the case of Meerkat, if there's an error, then unless keep alive is enabled, then it will shut down. So there's some similarities and some differences between the two. So we can repeat what we described earlier, where we run an abstract interpretation and extract these cat expressions that represent these different programs. Notice here we've introduced, again, Boolean test symbols that correspond to whether an error has occurred and to whether keep alive is enabled. Okay, so we'd like to synthesize the trace refinement relations. We ask whether... we ask whether the one's contained in the other or the conditions under which, and that leads us to wanting to know whether there's a trace refinement relation. So what we can do is start, since we're working with cat, that means we have this convenient equational theory, and we can leverage Damien Pou's SimCat tool to check whether the one cat expression is contained in the other. And conveniently, in this case there isn't, and conveniently the tool gives you a counterexample. That is, it gives you a string of possible behaviors of the first program that are not in the second program, and vice versa. So for example, you can have the behavior where an error happens, but then keep alive is turned off in the first one. And in the second one, you could have a behavior where an error happens, but then the clear connection and shutdown events happen. So now we're in this tricky situation where we have these two different behaviors, and we'd like to find some correlation between them. And in a way, it kind of sounds like an edit distance problem, because you're trying to find this correlation between two different strings, right? So in edit distance, as a reminder, you're trying to find the closest relation, such as maybe in a search string or something like that. And when edit distance, you come up with a sequence of transformations, like replacing characters or removing characters. And after you apply that to the string shown at the top, then you reduce it to two equivalent strings. But in this context with these trace classes, it's more like an edit distance over trees rather than strings. And the types of edits that you do may be a little bit different. So for example, you typically don't insert a new symbol into a program. And also some types of transformations are more heavyweight than others. Like replacing a symbol seems like a big deal if you're talking about a program, whereas it's a far less big deal if you just set a test symbol to be true. It's like a sort of case split. Okay, so what we do then is from these counterexamples, we have a custom edit distance algorithm that will suggest different ways in which these counterexamples can be massaged to be equivalent. And for this particular example, one way is to simply remove this condition of the keep alive not being negative. Or we could try to remove some of these events that occur in the second counterexample. And in this case, what we do is we have some choices that can be made. And as I said a moment ago, the simplest thing to do is simply case split on one of these Boolean conditions, because then we can start to break this down into different classes of traces. So whenever we see that the edit distance algorithm suggests removing a Boolean test symbol, we instead can case split on that test symbol. So this is how the algorithm proceeds. When it determines that there's one it can case split on, it now does that. It takes this condition, in this case the keep alive, and then we can instrument this keep alive into the program, rerun abstract interpretation on the program, and now obtain a more refined trace class. So then we can repeat this process. We've simplified K1, but they're still not equivalent. So again, we use SymCat to ask whether or not they're equivalent, and we get counterexamples. This time, edit distance only says that the only thing we can do is remove the clear connection event from counterexample 2. So we can do this by introducing an axiom or hypothesis into the cat that says that the clear connection is equivalent to skip. Having done that, we obtain, as this part of the search tree, the first tuple that will go into overall trace refinement relation. And again, it's of the form R1, R2, A. So the first one says restricted to cases where a keep alive is less than 0. And then the R2 is just any symbol is permitted. And then the axiom that we've introduced is that the clear connection is equal to skip. And now we have to deal with the other case, which is when the keep alive is not less than 0. So we sort of proceed with that, and I won't go through the details, but we end up finding one other tuple that we can add to the trace refinement relation. So I've skipped a lot of details here. The different sub-procedures can be found in the paper. You have to be careful with the abstraction and refining abstractions and combining abstractions. But I've given kind of the high-level picture. So the last thing I'd like to do is discuss our implementation in a new tool called Nautical. Nautical is written in OCaml, and as I've been mentioning, it's built on top of abstract interpretation, interproc, and SymCat. It's freely available on GitHub. It's easy to run from the command line, and the artifacts available, it's reusable and functional. We created some benchmarks for this. There weren't really any existing ones that were kind of relevant. And these do a variety of things, some that just exercise the various technical aspects of the theory. We also created some that model I/O and system calls, acquire, release, and then some more complicated ones that involve iterating over arrays and so forth. And we ran experiments using a MacBook Pro, and the results are this big table, which you can't see, so I'll zoom in. So the first couple of benchmarks are shown here. We report the lines of code and the number of events that are in it, as well as the direction. As I said, you can either do it for equivalence or inclusion. And then we report the amount of time it took to synthesize trace refinement relations and the number of solutions that were generated. So as you're going through this algorithm, there are lots of choice points, and because of that, we record multiple possible solutions. So there's one case in particular called zero impos, and in this case, we permit the user to specify events that one cannot remove. And in this particular example, there's no way to create, to massage the one program so that it gets contained in the other. So it's correct that there are 0 solutions. We also report some statistics about the output of the tool. So we report the number of tuples that are in the solution that has the minimum number of tuples, as well as the maximum number of tuples. We also report the number of hypotheses that were introduced in the solution that has the minimum number of hypotheses, and similarly for a maximum. And this gives you a kind of sense of quality of the result. Ideally, we'd like to have as few hypotheses as possible and rather focus on being able to sort of case split. Then we looked at some slightly bigger examples that I've been mentioning with some more lines of code. And again, pretty much in all cases, solutions can be generated fairly quickly, often in less than a second. There are some where it gets a little bit bigger, and there are some cases where the number of solutions starts to get large, and this happens when there are many conditionals, and so the search space kind of blows up. So in summary, we showed that we can promptly generate these concise trace refinement relations. There was not too much correlation between the number of lines of code and the running time, but more the correlation with the code complexity. So if a program had lots of events or lots of branching, then that led to more time. And in conclusion, we've described trace refinement relations for describing similarities and differences in the way two programs behave in terms of their traces. We described algorithms for synthesizing these trace refinement relations, and this employs a custom edit distance algorithm for correlating across programs. And there's this tool called Nautical that we've implemented that shows that we can generate them promptly. In the future, we'd like to look into interprocedural reasoning over CAT and scaling Nautical to industrial examples and incorporating these kinds of techniques into build tools. Thank you very much, and I'd be happy to take questions.
Okay, well, I have a question. So you used CAT as your basis for doing all of your reasoning, which has its own limitations in terms of things like infinite executions. How much of this would be reusable to switch to something like Omega Automata or some other abstraction with maybe more power, but also some effective decision procedures?
Right. Yeah. So for this work so far, we focused only on finite traces. As you mentioned, CAT can only express those. Going beyond that, there are more elaborate theories of CAT, like clean algebra with domain, and I can't remember the name of the other one. But that's definitely something we'd like to explore in the future, is different types of trace languages that can describe more elaborate behaviors.
Anybody else? We have time for one more one. Okay, well, let's thank Eric again.